In material science, hardness is defined strictly as a material's mechanical resistance to localized plastic deformation, its ability to withstand being indented or scratched. For decades, traditional testing frameworks like the Brunel and Vickers protocols were the standard methods used to quantify this resistance. These legacy methods operate by driving an indenter into a material and then calculating hardness based on the two-dimensional surface area of the resulting crater left behind. Measuring that area requires secondary optical analysis. A technician must place the material under a microscope, measure the precise diameter of the crater, and calculate the final value. This makes the process slow, tedious, and highly dependent on human exactness. The Rockwell Hardness test was engineered as a direct solution to this industrial bottleneck. This split-screen diagram illustrates the mechanical divergence. While traditional methods rely on optical area, the Rockwell system measures the linear depth of penetration. By isolating depth as the sole variable, the system allows a machine to bypass the microscope entirely and output an instantaneous hardness value the moment the test concludes. Achieving that speed accurately across thousands of different materials requires complex mechanics. The system relies on a strict two-stage loading protocol and 9 distinct physical testing scales. Shifting the measurement metric from optical area to mechanical depth elevated the Rockwell test from a slow laboratory exercise into the most rapid-fire quality control tool in mass production. Measuring microscopic depth directly introduces an immediate physical obstacle: surface roughness. Even polished metal possesses microscopic peaks and valleys. If a machine were to measure depth from the very top of a microscopic peak, the resulting hardness value would be wildly inaccurate. The Rockwell protocol corrects for this through Step 1, the application of a preliminary minor load, calibrated precisely to 10 kilograms of force. This cross-sectional diagram shows the mechanical purpose of the minor load. It crushes through those microscopic surface imperfections to establish a flawless preloaded baseline. This straight baseline is the zero datum line, the verified starting point. Next is the major load. Up to 150 kilograms of force drives the indenter deep into the material's internal lattice structure. This major load induces the true permanent plastic deformation of the target material. In Step 4, the major load is removed, but critically, the 10-kilogram minor load remains applied. Removing the major load allows the material to undergo elastic recovery. It naturally springs back upward slightly. By waiting for this rebound, the machine isolates only the permanent plastic deformation. Finally, in Step 5, the machine calculates the total vertical distance the indenter traveled between the initial zero datum line and the final resting depth. The reading is governed by an inverse physical law. A deeper penetration indicates a softer material. Conversely, a shallower penetration yields a higher number, indicating a harder material. The efficiency of the Rockwell protocol lies in mathematically isolating permanent structural deformation from irrelevant surface errors, using this highly regulated two-step sequence. A secondary mechanical problem arises. You cannot use the exact same indenter and force to test both a brittle carbide tool and a soft plastic. Applying maximum force to brittle materials causes catastrophic shattering. Conversely, using a sharp diamond indenter on soft metals causes complete puncture, rendering the test useless. The solution is the Rockwell scale matrix. The matrix consists of two key variables: applied load force on the x-axis and indenter geometry on the y-axis. The intersection of the diamond cone and the 150-kilogram load creates the standard scale, HRC. HRC is the heavy-duty standard explicitly reserved for hardened steel, heavy gears, and industrial dies. However, testing a thin carbide blade with the extreme HRC load would crack the specimen instantly. Dropping the load to 60 kilograms while keeping the diamond indenter creates scale A, or HRA, calibrated for brittle materials. If we test soft aluminum sheet metal, the sharp diamond point would pierce right through the specimen, regardless of load. Swapping the diamond for a blunt 1/6-inch steel ball and applying a 100-kilogram load establishes HRB, the solution for yielding soft metals. The remaining permutations cover the extreme edges of material vulnerability. Combining the 1/8-inch ball with 100 kilograms gives us HRE for cast iron, while pushing the load up to 150 kilograms creates HRK, tailored for plastics. An HRC or HRB rating is a declaration of the specific, tailored physical constraints required to successfully test a material without destroying it. These specific scales dictate structural survival on the manufacturing floor, particularly in metallurgy, where metals are tested immediately following intense heat treatment processes. In the automobile industry, Rockwell testing ensures that critical engine parts, axles, and crankshafts can withstand high torque without shearing. In the tooling industry, it verifies that drill bits and milling cutters possess a hardness rating strictly superior to the materials they are designed to cut. Reviewing this summary graphic of core principles, the first essential takeaway is that the Rockwell system is defined entirely by measuring indentation depth, completely eliminating optical area analysis. Second, the accuracy of that depth measurement relies entirely on the two-stage protocol, utilizing a minor load to crush surface roughness before the major deformation load is applied. Third, of the 9 possible test permutations, Scale C, or HRC, remains the undisputed standard for measuring industrial hard steels. The Rockwell protocol demonstrates that understanding a material's physical limits requires the precise mathematical pairing of geometry and pressure.